Assalamualaikum and good day to everyone. So this time I will talk about another chapter from our subject, which is enzyme technology, and it is on the safety and regulation of enzyme. So included in this chapter is the topic preparation of enzymes for sale. So we want to see what are the things that we need to do before we can put the enzymes for sale. Okay, so once the enzyme has been purified and concentrated, we need to retain the activity. So we have covered a little bit of the how the activity correlates with the enzyme stability and what are the factors affecting the enzyme activity and stability. Okay, so the objective for the manufacturer is to retain the enzyme activity after all the purification and concentration process. So because it is important because they are sold on the basis of the overall activity. So often the enzyme will have a higher activity than that stated by the manufacturer. Why? Because it wants to ensure that the enzyme that we sell has the guaranteed storage life. So a higher activity will be best to ensure that your consumer or your client get the enzyme with the guaranteed activity. And along with that, the manufacturer will recommend the storage condition as well as the expected rate of loss of activity under those storage conditions. So there will be a loss of enzyme activity over time. So this will need to be tested by the manufacturer before he can sell it. All right. So again, retention of the enzyme activity is important during the prior to sale and after that. So to achieve this stability, the manufacturer will have its own formulation to achieve stability. So formulation is often kept secret because if the enzyme is produced by different manufacturer, then this formulation will provide them with the competitive edge over all the rival companies. So even if it need to be revealed to the client, then you may get a confidentiality agreement. So this will protect the manufacturer in order to provide the company an edge over the rest of the other companies. So you need to remember that most industrial enzymes contain relatively little active enzyme, so less than 10% weight over weight. So the rest of the bulk comes from this the preservatives, the stabilizers, the bulking agents, inactive protein, salts, and also the buffers or the diluents. So this will allow standardization between different batches of enzyme produced by the same manufacturer. Okay. So what are the approaches to maintain the enzyme activity? So there are three approaches here. One is by additives, covalent modification, as well as enzyme immobilization. So for enzyme immobilization, I can see that this has been covered extensively in fermentation subject. Please correct me if I'm wrong, but we won't be covering that approach, this one in this subject. Yeah. So the key to maintain the enzyme activity is to maintain the conformation of the protein of the enzyme. So how we can do that? By preventing unfolding, aggregation, as well as changes in the covalent structure. Okay, so in general, protein are stabilized by increasing their concentration. So highly concentrated enzymes are more stable than highly dilute protein or enzyme. So if you concentrate your enzyme prep, that will be good, as well as the ionic strength of their environment. So anion, cation, the salts affect the enzyme stability. Why? Because it competes with the proteins for water, to interact with water, and also to bind to charge group or dipoles. So you can see this interaction happening if you add different type of ions, anions, cations, and different types of ions can strengthen the hydrophobic areas. So you can have the enzyme more resistant to thermal unfolding reaction, because all the hydrophobic areas which may be attacked by thermal unfolding is protected. So we have these two terms, which is enzyme stabilizer and enzyme destabilizer. So enzyme stabilizer is effective in stabilizing hydrophobic interaction, whereas enzyme destabilizer disrupt or destabilize the enzyme by disrupting the localized structure of water. So this is an anti-stabilizing effect. So this is called the chaotropic effect. Alright, so the next slide explain this a little bit more. So here is what they call the Hofmeister effect. So you can see there's two arrows there. So if you have different types of cations or different types of anions here as well, it can either increase the chaotropic effect, which means destabilization of protein, or it can increase the stabilization effect, where a enzyme gets stabilized. Okay, so there are different types of anions and cations that we want to use for stabilizing our enzyme. So some examples below the table. So ammonium sulfate and potassium hydrogen phosphate are recognized as a powerful enzyme stabilizer. So you can see here hydrogen phosphate, sulfate, so it increase enzyme stabilization. So here as well, ammonium, potassium. So these are two cations that are at the stabilizing effect, as opposed to the rest of the other cations that actually increase the chaotropic effect. Okay, and another example, calcium chloride. So calcium is a cation that increase the chaotropic effect, thereby destabilizing the enzyme. Okay, and then there are also other example. So here calcium as well as cobalt have are example of cations that stabilize some enzyme. So here said cobalt stabilize glucose isomerase. Sorry, I'm doodling very badly. And calcium stabilize alpha amylases. All right. So let me see how long. Okay, we can talk a little bit more before I stop. Other examples of things that you can do to stabilize your enzymes are by adding low molecular weight polyols here. So what are examples of these low molecular weight polyols? Glycerol, sorbitol, and mannitol. They can be added for to stabilize the enzyme. So how do they stabilize the enzyme? By repressing microbial growth, reducing water activity, as well as to form a protective shells to prevent unfolding processes of the enzyme. Another thing you can add in to your enzyme mix is glycerol. So glycerol protect enzyme against denaturation when you store it at sub-zero temperatures, -80 for example. So when you add glycerol within the enzyme solution, then it will protect it from the ice crystal formation, and thus the protein will not denature due to that. So ice crystal formation in the enzyme structure can destroy the enzyme conformation. So that's why we don't want that. And some other hydrophilic polymers can also stabilize the enzyme. How? By replacing the enzyme interaction or enzyme water interaction with less denaturing enzyme polymer interaction. Okay, and it also have a stabilizing hydrophobic effect within the enzyme. Next is using site-specific mutagenesis. So this is observed by comparing enzyme with residues in mesophilic and thermophilic organism. So mesophilic and thermophilic organism have a lot of arginine. So if we compare it with non-thermostable organism, it has less arginine compared to lysine and histidine. So arginine is good because in terms of stability, because thermostability, because it can form stronger salt links with bidentate aspartate. So aspartate can bind to two atoms, as well as glutamate side chains. So these salt links will result in more rigid structures of the enzyme. However, we need to remember that there's limitation on this. If you mutate lysine and histidine to arginine, where it can have a lower activity, so Vmax, than the natural enzyme. So you may need to consider this before you perform site-specific mutagenesis. Okay, so I think we will stop here and continue with the next part in the next videos. Thank you.